Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The afternoon session, we have some excellent talks lined up. But first, we have something extremely special for you. Michael Littman is going to give us the premiere live performance of his machine learning adaptation of Michael Jackson's Thriller. So if you Google machine learning a cappella, then you will see Michael Littman singing Michael Jackson's Thriller, overfitting. Yeah. But first, he's going to give us a research talk instead, I think.
All right. See that coming. But it is true. I just released the video yesterday, so you feel free to go and check it out. But I am not going to perform it live. All right. Anyway, thanks a lot for coming, and for the organizers giving me a chance to talk. We decided it would be maybe okay to give kind of a reinforcement learning talk at a kind of a tutorial level, because probably that's not where most people are coming from. So depending on how you think about these things, this is going to be a narrow talk, or a talk about absolutely everything, because it's about acting in multi-agent environments, which is what we do all the time. This is what we do. We interact with people. I'm interacting with you right now. All right, so or you could think of it as, well, within machine learning, there's reinforcement learning, which maybe not a lot of people do. And within that, this is multi-agent reinforcement learning. So maybe that seems narrow. But I think it's actually really cool, and it's worth thinking about, and thinking about how this could interact with other aspects of machine learning as well. And I had a little clicker thing, but I don't know if I do anymore. I'm going to use the space bar. All right, so let me start off by kind of setting up the classical reinforcement learning setting, and then we'll move over to the multi-agent setting as we go. So here's, for whatever reason, there ended up being a Mario theme. So there's Mario, like from the video game, and for whatever reason, he's trapped in a grid world, and just like many reinforcement learning researchers. And what Mario's trying to do is trying to get to one of these red goal states. It's red to match his, let's say, hat. And he can move up, down, left, right in the grid. He can't move through these sort of heavier lines. Those block his motion. And these ones that are kind of dashed a little bit, like half heavy, half light, it's like 50% probability that Mario will be able to get through those. So if he tries to go through it, it might fail and he'll end up where he started, or it might succeed and he'll end up on the other side. So can you look at this and figure out what his optimal strategy would be to get to a red goal? All right, wait, Eric's going to tell us. All right, so he should go to the right. Oh, sure, that would be the first action. That's not a bad choice. Which goal is he going to go for? Or is it all contingent? Could be contingent. This one? This one's nice and close. So what is the expected number of steps that it takes to get to the close goal, this goal here? So, well, it depends on how you do it. But one way to do it is to go here, here. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That was expected values. That's what I was doing with the double hit. So 15 steps to get to that goal. Did anybody find anything better than that? Top right, the farthest one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, so what's my point? My point is I can make a grid to fool you. It's not clear that that's an important point to make, but that is the point that I was making with this. But I wanted to get across a couple of things. One is that, that it has all the elements that we need to define a reinforcement learning problem. One is the states. In this case, it's positions in the grid. But more generally, it's going to be whatever state, whatever aspects of the environment are important for decision making. So it could be how tired he is, and whether there's, I don't know the right words, Goomba maybe, like baddies that are prowling around in the grid. Maybe even what his goal is. It might actually change and therefore needs to be part of the state. There's states, there's actions, which is what moment to moment he is capable of doing, which in this case is the up, down, left, right. There's state transitions. So what's the probability that if Mario chooses to go to the left, that he'll end up in this grid cell on the next step. And there's the reward function, which in this case, there's a payoff for getting to one of the red goals, and otherwise maybe a small cost for just wandering around in the grid, consuming energy. So, so that's the essence of an idea. This is what most of reinforcement learning is about, one way or another. Usually it's not quite so large a grid. And see, that's just not nice to my feel. I'm sorry. But one thing that you can notice about that is it's kind of a lonely place to be, Markov decision processes, right? Because there's little Mario in the corner, and then there's just all this empty space, just wandering around Cambridge, and there's no humans. So the idea of multi-agent reinforcement learning is learning what to do given that there's other critters also prowling around, let's say in the grid, also trying to decide what to do. All right, so so that's what we're going to get to. But first, I want to point out, if you haven't seen this sort of thing before, how do we actually go about solving these things? How do we solve these kinds of sequential decision problems? In this case, it was formulated as a Markov decision problem, or Markov decision process, which, as I said, states, actions, rewards, transitions. Usually, we'll throw in a discount factor to help make things mathematically helpful. And it's all about the interaction between the agent and the environment. To solve these things, one of the ways that we can do it, if you know the entire environmental model in advance, you know what the states and actions and rewards and everything are, you can solve this system of equations called the Bellman Equations. And what they tell us is associated with each state and an action you could take in that state, what's the immediate reward going to be, plus the discounted expected value of the state that you end up in for taking that action, of the value of the state you end up in, which is going to be the maximum over all actions you could take there of, again, this Q value in the resulting state. So, there's Q's on both sides, so it's not completely trivial to solve this, but we know lots of ways to do it. It's not a big deal. And if we solve it, if we actually have a solution to this, we know how to behave optimally. What we do is each time we're in some state st, say state st at time t, we're going to choose the action that has the highest Q value. It has the highest expected future and present reward for taking that action. So that's the solution. If you don't know the reward and transitions in advance, you could learn them, right? So you can wander around in the world and try to learn a mapping from state and action to reward and state and action to next state. Or you can do tricks like Q learning, which tells us that what we're trying to do is each time we take a step in the world, we have estimates of these Q values, and we just change them a little bit so that they're a little bit more like solutions to this. So that's the essential idea for single agent reinforcement learning. As I said, there's a couple different ways of solving these. Policy search is another where you're actually trying out different ways of behaving and see how well they actually work. Value-based methods are trying to estimate this Q value and iteratively improving it using experience. And model-based approaches say, okay, we're going to do something more akin to supervised learning, which is to learn directly a mapping from state and action to next state and reward. This is a nice learning problem in the sense that each time the agent takes a step in the environment, it gets a sample. It gets an example of what the reward was, the immediate reward was, and what the state transition was. This, which is more commonly done in the community, is a much harder learning problem in the sense that what you're trying to do is predict what future Q values are going to be, but those are a moving target. As you're moving around in the world and making improvements to your Q function, you're trying to train towards that, but you're also trying to train that. So this can be very, very messy, and it's hard to get formal results that say that you're going to do the right thing. Here it's not so bad, at least in principle. All right, so what I'd like to do is move us to the multi-agent setting. So the multi-agent setting is really hard for a bunch of reasons. One is it's kind of not entirely necessarily clear what it is you're trying to do. So let's say that we're still trying to maximize reward. That seems reasonable, right? We still have some notion of a reward function. We're still trying to find a way of behaving that makes us as happy as possible. Okay, that's as fine as far as it goes, but it's still not completely specified. What we're going to do is imagine that there's, okay, so here's Mario again. He's us. And this is Luigi, right? Luigi, he's another guy in the environment. But let's imagine that he's also like us, right? So he also has he's a set of actions. Transitions now are actually dependent on the actions that we both choose. So both of us are going to get to choose an action, and what happens next depends on what we both decided. And we both have our own reward functions. So Mario's getting paid off for the actions that happen, and so is Luigi. And Mario's actions, can depend on Luigi's choices as well, right? So I don't have complete control over my own rewards anymore, right? I'm kind of dependent on what the decisions are of my partners in the environment. So here's a little grid world example just to think through how this goes. So what we're trying to do is, again, we can go north, south, east, west. The walls are the same as they were before. Mario is still trying to get to red because of his hat. Luigi's still trying to get to green. Well, Luigi's trying to get to green because of his hat. What should we do? Right? It was a little bit subtle before because it was complicated. Now the grid is really easy, right? The shortest path for Mario is, well, any of a number of paths. Take a shortest number of steps to get to the goal. What's the problem? The problem is we don't know what Luigi's going to do. So what do we do? How do you do this in general? So Mario could choose to go to this square on the first step, but Luigi could also have chosen to go to that square on the first step. So that doesn't seem so safe, right? So maybe Mario should go up one, because that's en route to the goal, but definitely isn't going to collide with Luigi. So that's good. Now Luigi could reason the same thing, and now in the very next step will be here, which is kind of the same problem that we were in the beginning, except one more step closer to death. So it's not exactly clear. Okay, well, what do we do then? We could do the same kind of reasoning, and Mario ends up in the green, and Luigi ends up in the red. And now we're really in trouble, because now there's no way they can both follow the shortest path. So it would be nice if they had kind of worked it out earlier. So I don't know. It's not. So maybe the punchline of this talk is, I have no idea. So moving on. All right, so there's a little collision. From this state, it's still not quite clear what you should do. Certainly, well, let's see what happens. All right, well, Mario ended up trying to go that way and Luigi the other way, and they missed each other, and that's great, because now they can just follow paths to the goal. Oh, wait, I forgot to tell you. As soon as anyone gets to the goal, the game is over. So in this case, Luigi got his 100 points for getting to the goal, and Mario is done. Nothing, sadness. So they can both get the 100 if they both get there at the same time, but they didn't. So that was kind of a bummer for Mario. So now there's sort of an interesting thing going on, right? So they can be a little bit cooperative in that they can both get high reward, or they can be a little bit competitive. They can get in each other's way and prevent the other one from getting reward. It's not a zero-sum game in the classical sense, right? Where it's not that Mario lost because Luigi won. It's that Mario lost because, well, Mario lost, right? And Mario could have won even though Luigi won. All right, so when we try to actually define something like the Bellman equations for these kind of games, what we realize pretty quickly is it's going to depend a lot on what we think the other player is going to do. And so if we're thinking now kind of in terms of the literature on this problem, you get lots of different algorithms popping up depending on what you think the other player is like, which is kind of unsatisfying. But let's just go with that for a minute. Let's imagine that there's lots of different personalities that the opponent could take. Mario doesn't know which one it is, but Mario's just going to commit. It's going to pick one. And depending on the assumption about how the opponent is going to choose actions, we actually get something like a Bellman equation with a different operator here that this used to be a max in the other equation. Now it's, kind of depends on what the other player is going to do. So the Q value to Mario, Q1, in some state, given a pair of actions for the two players, is the immediate reward to Mario for that pair of actions. That part's easy. Plus the discounted expected value of the next state that they end up in together. And what happens in the next state? Well, I don't know, but it's going to have a set of Q values associated with it. And we have to somehow summarize them. So this operator is just a generic operator where I'm saying, let's just summarize. And we're going to look at what different possibilities are for this slot. They come from different assumptions, and they lead to different algorithms and different results. So if we assume, for example, that the partner is this some kind of fixed sort of Markov chain type agent, and we know what it is, then it's really easy, because what we can do is we can take an expected value over the actions that other player is going to take, because it's just following whatever it's following. All right? And so then this operator, this summarization over the value in a state, ends up being, I'm going to choose whatever action's best, given that my opponent is choosing randomly according to this distribution. So you can do that and solve it. It just turns it back into an MDP. All is well. If everyone could just be fixed and tell me their strategy, the world would be easier for me. All right. If the partner is like that, but actually has its own internal state, it's not basing its actions just on the current state of the environment, but also, its mood or things that have happened in the past, now it gets bad. It's a partially observable Markov decision process if the behavior is known. It's a POMDP learning problem if it's unknown. We don't really know how to solve those. So Yeah, so there's that. All right, so, but there's other things we can assume as well. So we don't have to assume that they're sort of, mindless robots that are doing whatever they're doing. We could assume, for example, that they're really, really helpful, like Princess Peach would probably be. So Princess Peach is, our assumption, our Princess Peach type assumption says, my opponent is going to choose whatever action is going to make me most successful, all right? And so that substitutes this summary operator with a max. Right? So of all possible joint actions, we will choose the thing that's best for me. Right? Super helpful, very easy to compute. It turns it, again, back into an MDP where essentially I'm choosing actions jointly. I'm choosing actions for all of us, which is great, but kind of unrealistic. Maybe we should be computer scientists about it and think worst case. So worst case, this is like thinking like AI people, best case analysis, and this is like thinking like theoreticians, worst case analysis. Worst case analysis says, I assume that whatever the opponent is trying to do, he has no concern for his own welfare, as, by the way, neither did Princess Peach. His only concern is to make my score low. All right? He's out for blood, my blood. That turns the summary operator into a minimax, right? It's saying, I'm going to choose whatever action's best for me, given that the opponent is trying to make my score as low as possible. This is a well-defined operator. You can solve it with linear programming. Things work out sort of nice. But again, it doesn't feel entirely realistic, right? So let's go back to that grid example and see what happens. Actually, a slightly different grid. This is a grid, well, anyway, this is a grid that turns out to be surprisingly interesting given how small it is. So here, Mario's trying to get to the red. Princess Peach is trying to get to the pink. It might not be so visible, but there's walls around these colors. So the only way into this red thing is to come from where Princess Peach is standing. The only way into the pink thing is to come from where Mario is standing. All right? So we're kind of in a standoff right from the get-go. So what does the Princess Peach assumption get us for this, the so-called friend queue algorithm? It says that, well, Mario's trying to maximize reward, and Princess Peach is trying to help Mario maximize reward. So the strategy ends up looking like this, right? Princess Peach gets out of the way, after you, right? Or not even after you. When you're done, it will all be over. And then Mario scores, and and all is well. All right? This is an imagined situation, right? Because we don't know that it really will play out that way. But Mario computes his values, computes his policy under the assumption that something like this is going to happen. In this situation, though, it's quite different. What's going to happen? So let's see. So we'll reset that one, and now this is what the strategy looks like for the second game, right? So Mario thinks, okay, Bowser. Anybody? Do we know? Dragon creature, bad dragon creature, is trying to hurt Mario. Mario is trying to get to Mario's goal. Bad dragon creature doesn't want that. So bad dragon creature just parks in front of the goal, effectively blocking Mario permanently. Mario at this point thinks, okay, well, if you're just going to block me, I'm not going to waste any energy moving around. I'm just going to die here. I'm just going to stand here forever. So this is the optimal strategy under the assumption that you're up against this sort of Bowser-y character. Again, we can compute this. We have reinforcement learning algorithms that will converge to this solution. And then when you actually try them with other agents, they do terrible things, like, right? Or like, I'm just going to walk to, hey, what are you still in my way for? I'm expecting you to get out of my way. They play terribly. All right, so what do we do? Well, so there's an answer to this kind of question. What do you do when there's two different players and they have their own feelings? This is, as far as I know, the only result that has won both the Nobel Prize and the Academy Award for Best Motion Picture, and that is Nash Equilibrium. So the idea of a Nash Equilibrium says, we're going to try to find jointly a way for us to behave so that we're both as happy as we can be, in the sense that if you stay fixed, I'm doing what's best for me. If I stay fixed, you're doing what's best for you. It's a natural enough kind of concept. The equilibrium aspect of it is the idea that once we're there, there's no incentive to change. It might be hard to get there. In fact, we think these things are very hard to compute in general, especially in these sequential grid games. But nonetheless, maybe this is a concept that we can go for. And in particular, it gives us a way of thinking about, once we're in a new state, how should we summarize the value? Let's use the value of a Nash equilibrium. So that's an OK idea. Let's see. So am I going to animate this? Apparently. All right, hang on a second. I want to lead up to it. So apparently not. Apparently I'm just going to animate this. All right, so let's look at this game. So what's a Nash equilibrium for this game? Well, the Bowser thing is a Nash equilibrium. If the if Mario thinks Luigi's not going to move, then Mario's best strategy is to not move. If Luigi thinks Mario's not going to move, then Luigi's best strategy is to not move. That is a Nash equilibrium. It's not a great one, but it is what it is. The Princess Peach thing is not a Nash equilibrium, right? So the Princess Peach thing says, so Mario's just going to start going for the goal. Of course, Luigi might start doing that as well. They're going to collide in the middle. Given that Mario's trying to get to the goal, Luigi's best strategy is not to get out of the way. It's to stay put. All right. So this is not a Nash equilibrium. What is a Nash equilibrium? So I was very surprised. The algorithm I'm about to tell you found this solution, which I purposely tried to make not a solution, but it actually turns out to be a solution. So what's going to happen? Well, let's take you through step by step. So in the first step, Mario starts heading to the goal. Luigi stands in Mario's goal. OK, that doesn't seem like that's going to go particularly well. Mario continues towards his goal, and then misses it, and then takes one additional step into the corner while Luigi comes out of the goal. What's the situation we're in now? Mario is 1, 2, 3 steps from Mario's goal. Luigi is 1, 2, 3 steps from Luigi's goal. They can now proceed happily towards their respective goals. If each player is, if Luigi adopts that strategy, that was Mario's best response. If Mario adopts that strategy, that's Luigi's best response. This is also a Nash equilibrium, but it's a much better one than the just sitting on your butt one, right? So this is actually really cool. I thought this was a bug for a long time, but in fact, this is a very reasonable strategy. Like, it seems like they're way too smart. The thing that I think is really cool is it's this step here. When Mario's here, right? Why should Mario continue going away from the goal? It has to go back to the goal at one point. Why doesn't it just wait there? Why? Why won't Luigi move? Because it's threatening, right? So if Luigi comes out to here, Luigi is 1, 2, 3 steps from the goal, and Mario is 1, 2 steps from the goal. Luigi starts, booking it towards the goal, and Mario's like, ding, game over, right? So Mario has to do one of these, right? Like, it's okay. Look, I'm not a threat to you, and now we can proceed. Right? It's like you see these things on TV sometimes where they're like pointing guns at each other. You have to put the gun down and back away from the gun, right? You can't just be like, no, you put the gun down, right? Because no one's going for that. So it actually converged on that solution completely on its own. I mean, whatever. It followed its algorithm. Right, because it's not safe for Luigi. So Luigi won't move, so Mario won't get his score. So it's better for Mario to go all the way out and be clear. It is a better strategy in the sense of maximizing the total expected reward, but it's not a Nash equilibrium because it's not safe for both players. All right, anyway, I particularly like that example. All right, so the Nash equilibrium algorithm says that what we're going to do is summarize the values in a state by computing the Nash equilibrium, backing that up. So this turns out to be problematic. So for one thing, you need access to your partner's values to compute that. Maybe that's not so bad. I can learn about what I'm doing. I can learn about what you've learned. That should be all right. But unfortunately, it's not a non-expansion. It's not a summary operator that actually is guaranteed to converge, to go to a fixed point. And in fact, there's multiple answers, right? So during the algorithm, it can be faced with a set of Q values that have multiple ways of computing Nash equilibria with different values. Which one should it pick? The highest one, the lowest one, the middle one, a safe one? It's not really clear. So the result of this is that it doesn't necessarily converge. Sometimes it just doesn't converge. And in fact, this isn't just a little thing that we're going to be able to get away from. This whole idea of using Q values to decide what to do in multi-agent environments can't work. This is a fundamental limitation of this class of approaches, which I won't get to give you the whole proof of, but Marty Zienkiewicz came up with a really simple game. He calls it the owl game. I don't know. So he added the owl. I put in the Luigi characters. It's now complete mixed metaphor. I have no idea how to think about this. But I did find a Mario owl, so it makes it a little work. But this is a little MDP, a little two-state problem, where in this state, Mario gets to make the decision, and in this state, Luigi gets to make the decision that has no deterministic Nash equilibrium. The only Nash equilibrium in this tiny little game have the property that both players have to randomize. Now, usually we think about randomization as something that you have to do because of simultaneous moves in a game, like the matching pennies game, right? Or rock, paper, scissors. If I always throw a rock, if any deterministic strategy in rock, paper, scissors is going to get trounced, right? But if you're not trying to fake out the other player, what's the point of using a mixed strategy, being probabilistic, it turns out that it's necessary to get everybody's values to kind of equilibrate. And so that's what ends up happening in this little game here, that if Mario does something deterministically, the best response to that is for Luigi to do something else, for which the best response is for Mario to do something different. It can't stabilize. The point of this example is that means that because there's only one action in each of these states, no matter what Q values you give me, I'm never going to derive from that a stochastic policy. The values are not enough information to decide what to do. You need something about the whole picture. And so this whole idea of using Q values to decide what to do, just like it can't work in this game, it can't work therefore in general. So that was, I guess, a punchline. I've got 15 seconds. Is that true? I have 15 seconds? All right. So in COCO values. All right, moving on. So COCO values are a result due to Kalai and Kalai. Do we have any Kalais with us? Yeah. All right. So they came up with this idea of mixing COCO, in addition to being delicious, is also a mixture of cooperative and competitive. And so what you do is to compute the value of a game, you say, well, what will we get if we work together versus what will we get if we worked separately? And let's use that separate value to actually determine side payments. Like, we're going to work together, but since you had the power position in the beginning, I'm going to give you some money to make it worth your while to do this thing that's best for both of us. We're going to maximize our pot and then split it in a way that's kind of fair. So they determined this idea. We applied it to sequential games, and actually were able to prove that a reinforcement learning algorithm in this setting converges. So that's pretty satisfying. It's not going to be the Nash, which is a bummer, and it's not going to be, it depends on this notion of side payments, which we don't always have access to. But still, it seemed like a cute answer to the there's just no way to solve this problem. All right, so just really quickly, this is what it does in this case. They end up paying each other to take risky moves, and then they go to the goal together, split the winnings. And all right, so last slide. Right, so standard reinforcement learning is kind of lonely, and if we want agents that are actually interacting in the real world, they have to deal with the fact that there's other agents in the real world. If nothing else, the other reinforcement learning agents that we finally fielded. So given that that's the case, we have to think about what it means to learn in that setting. There's often no right answer. Some of these games are unsolvable in a sense. Really, the right way to think about this is to keep in mind that multi-agent decision-making always takes place in a culture. It's not just a limitation that we have to guess who our opponents are. That's just reality. And we have to learn about what kind of opponents we tend to play with. Are we in a society where everyone helps each other or splits the winnings? Or are we in a society where everyone's trying to throttle each other? Your optimal action depends very much on the actions of others. OK, that was my talk. Thanks.
We have time for a quick question. I have a question. So it seems like a lot of these, a lot of this boils down to symmetry breaking of various kinds, and that there must be. I mean, on one hand, you mentioned that the sort of the random moves aspect of it. Is that enough in general to deal with symmetry breaking between both the different Nash equilibria, but also in in your first example, where somebody's kind of taking a top root and a bottom root?
Right, right.
Would that sort of solve that without thinking about these?
So. Yeah, I hadn't thought about it that way. It's interesting. So symmetry breaking, certainly in the case where the two agents had to choose paths that didn't bump into each other, but they crossed, it was all about, well, they both could do exactly the same thing. But we can even muck with that question and have it be asymmetric and still have to worry about symmetry breaking in a sense, right? If one agent was actually getting a whole lot more reward for getting to its goal and had a slightly shorter path, say, and the other one had a longer path, but could make some amount of money from it, it still might be the right thing for one to wait to let the other one go through. Maybe you need side payments or something, some kind of agreement. Maybe we're going to play this game again against each other tomorrow, and I might be in the other role, in which case I might want you to do well so that you'll be happy with me the next day. It's not just symmetry breaking. There's a lot of weirdness. Sean?
So is there any notion for how you can deal with, right? Like in that game you had, like maybe it's a strategy, I'm going to go to the goal, and I'm going to wait until the other guy goes to the furthest corner before I enter the goal to make sure like I'm optimal and you do the worst thing, and I have a threat that unless you do this,
Right. So there's some really interesting work in the context of repeated prisoner's dilemma, where if you're playing against somebody who learns, right? We care about learning. We're playing against somebody who learns and is just going to assume that I'm a fixed strategy and is going to adapt to me. Then the best thing that I can do is go right to the edge of cooperation, the littlest amount of cooperation that I can. You'll go along with that, I'll get a high score. So there are some really nice results saying that in many games you can actually do that. You can extract out of a learning agent the maximum amount that can be extracted before. Eventually it's like, no, forget you. I'm just going to go for myself. I don't get an additional reward by doing the thing that you're asking me to do. The problem with that is, of course, both agents could be in that mindset, in which case they're both extracting the maximum reward, in which case they both do horribly. It's like everything ultimately boils down to chicken. That's my feeling about multi-agent game theory is it tastes just like chicken. Right? So all the games end up having the property that you want to be the last one to learn. Right? If you show that you're a learning agent, then the other player can take advantage of you by adopting a strategy that when you adapt to it is best for the opponent. So you just want to show that you can't learn. Right? So they'll adapt to you and all will be well. But you don't. But you're both trying to do that. So you want to be the last one to look like you can learn. Right? Don't blink. Let the other one blink first and everything's better. So it's horrifying.
All right, let's thank Michael again.
All right. Thank you.